This video will define the basic circuit laws that are used in circuit analysis. Before we give the laws, we will start with some electric circuit definitions. A node is a point in the circuit that is connected to one or more elements. For example, if we have three resistors connected to each other, as shown on screen, then we have a node which is connected to all the three resistors. We can call this node A. We have another node B, a node C, and a node D. A branch is a simple element that is connected between two nodes. If we consider the following portion of a circuit, then we have three nodes. We will label them A, B, and C. Each of the resistors is a branch. For example, the first resistor connects between nodes A and B and is called a branch. And similarly, the second resistor which connects nodes B and C is also called a branch. A path is defined as starting from a node and passing through branches and nodes to the end node. If we consider the previous circuit diagram, then we have a path from node A to C through the two branches and passing through the node B. The last definition that we will consider is for a loop, which is a closed path where the starting and ending nodes are the same. We will show all of these definitions on the circuit displayed. It consists of a voltage source Vs and 7 resistors R1 to R7. Next, we will identify all the nodes in the circuit. The first node we will identify is the node A, which connects to three elements: the resistors R1, R4, and the voltage source Vs. Another node is node B, which connects to the resistors R1, R2, and R3. Node C, which connects to R2, R5, and R7. Node D, which connects to R4, R3, R5, and R6. And finally, node E, which connects to the voltage source Vs, R6, and R7. Each of the elements in this circuit are branches which connect two nodes. For example, R2 connects the nodes B and C and is a branch between B and C. There are many paths in this circuit. We will just give a few examples. For example, there's a path from A to B to C. Note that this path has two branches, one from A to B and another one from B to C. Another path, for example, may be A, B, D, E, C. Once again, note that there are branches between each two consecutive nodes in this path. Normally, we will keep the paths to be simple such that they do not cross through the same node more than one time. There are also many loops in this circuit. We will give a few examples. One loop is A, B, D, A. This loop starts from node A and comes back to node A and passes through branches and nodes. Once again, we will keep the loops to be simple such that they do not cross through the same node more than once, except for the starting and ending node, which show up twice in a loop. Another example of a loop will be A, B, C, E, A. Once again, note that a loop passes through branches as it travels from a node back to the same node. Once we have finished the basic definitions, we will go on to define the basic circuit laws that are used in circuit analysis. The first such law is called Kirchoff's current law, abbreviated as KCL, which is a statement of charge conservation. Consider the circuit on the top left, which consists of three elements connected to node A. And if we have, for example, 7 electrons going in to node A through the first element, 2 electrons leaving node A through another element. Once we know the number of electrons entering or leaving node A through 2 of the elements, we have no choice about the number of electrons leaving through the third element, which will be 5 electrons, such that charge is conserved at node A and the number of electrons entering and leaving the node A are equal. We also know that current is the differential of charge with respect to time, and thus if we have charge conservation at a node, we will also have current conservation at each node. If we consider the same circuit, which is given on the right hand side, this time with currents flowing in and out of the node A, Suppose we have 7.2 amperes flowing in from one element, 2.2 amperes leaving from another element. In this case, the current I, which will leave through the third element, will be equal to 5 amperes. Therefore, to have charge conservation, the current flowing in is equal to current flowing out of a node, which is the basic definition of Kirchoff's current law. We will apply KCL to another example. The current flowing into the circuit at the bottom is 5.1 amperes plus I, and it must be equal to the current flowing out of the node A, which is 2.2 amperes. We can solve this equation for I, which is equal to 2.2 minus 5.1 is equal to minus 2.9 amperes. The negative value of the current I indicates that the current is actually flowing in the other direction, and we can show that the current flowing out of node A through the third element is 2.9 amperes in the direction shown. To summarize, KCL states that the current entering a node must be equal to current flowing out of the node, which is essentially the same as charge conservation at node A. We can write KCL in many different forms. The first form is current entering a node is equal to current leaving the same node. We can rewrite this equation by writing both the currents entering and leaving a node on one side. For example, current entering a node minus the current leaving the node is equal to 0. Or current leaving a node minus current entering a node is equal to 0. All three forms of KCL can be combined into a single equation, and we can write that the summation of currents at a node is equal to 0, with the understanding that we assign the appropriate sign, either a plus sign or a minus sign, to each current when we sum up the currents at a node. Although we can use any one of the three KCL forms that are given above, it is customary to use a sign convention for currents. This sign convention is arbitrary but is followed by most books. The sign convention that we will follow is that currents leaving a node are given a positive sign and currents entering a node are with a negative sign, such that we can use KCL as sum of currents with the appropriate sign at each node is equal to 0. If we apply this sign convention to the circuit shown on screen, we have 4 elements connected to node 1, and we will write the KCL at node 1. Current I1 is entering node 1. It is given a negative sign, and we will write down minus I1. Current I2 is leaving. It will be with a positive sign. Current I3 is entering, a negative sign. And finally, current I4 is leaving, will be given with a positive sign, and this will all add up to 0. To summarize, you can use any one of the three forms of KCL given above. However, we will use the form with the sign conventions as shown on the screen. The second law that is used in circuit analysis is called Kirchoff's voltage law, and we will define this law next. Kirchoff's voltage law is abbreviated as KVL, and the basic statement of this law states that the voltage rise along any loop is equal to the voltage drops along the same loop. Consider this simple circuit shown on the left. It contains only one loop, and this loop can begin, for example, at node 3, go to node 1, then to 2, and then back to 3. As we move along this loop, starting from node 3 and going to node 1, we notice that we are going from the negative end of voltage V1 to the positive end. Since this is a voltage rise, we will write it on the left-hand side. As we move from node 1 to node 2, we have a voltage drop of V2. We will write this on the right-hand side. Finally, as we move from node 2 to node 3, we have another voltage drop, and we will also write this on the right-hand side. This gives us KVL for this loop, where the voltage V1 is equal to the sum of the voltages V2 and V3. Similar to the case of KCL, we can write KVL in 3 different forms. The first form is already given. The second form is to take all the voltages on one side and write the sum of the voltage drops along a loop minus the sum of the voltage rises along the same loop is equal to 0. Or we can write the sum of the voltage rises along a loop minus the sum of the voltage drops along the loop is equal to 0. You can use any one of these three forms of KVL. However, we will follow a sign convention for voltages, and the sign convention will be that voltage drops are given a positive sign and voltage rises are given a negative sign. This sign convention is arbitrary but is followed by most books. If we apply KVL to the circuit shown on screen, the loop can be defined as, for example, A, B, C, D, A, and the direction in which we are traversing this loop is shown. As we start from node A and move to node B, we have a voltage rise of V1. Voltage rises are given a negative sign. We will write down minus V1. As we move from B to C, we have a voltage drop, which will give us plus V2. From C to D, we have another voltage drop, plus V3. And finally, from D to A, we have another voltage drop, plus V4. And we are back to the node that we started from, so all of this is equal to 0. To summarize, you can use any one of the three forms of KVL. However, we will tend to use the form given on screen, which is to follow a sign convention. Voltage drops are given a positive sign and voltage rises are given a negative sign, such that the summation of all voltages along a loop is equal to 0.